Good morning, students. In last class, we have discussed about curves of acid-base titrations and redox titrations. Under redox titrations, you have studied about the redox indicators and different types of redox indicators. Under that, self indicators, external indicators, redox indicators, etc. So today we are going to discuss about precipitation titrations. Precipitation process of volumetric analysis are based upon the formation of insoluble precipitates when the reacting solutions are brought together. Thus, when a solution of silver nitrate is treated with silver chloride, sodium chloride or potassium thiocyanate, a white precipitate of silver chloride or silver thiocyanate is obtained. You can see here in the reaction silver nitrate which is added to the sodium chloride. We are getting silver chloride white precipitate sodium nitrate. In the same manner, silver nitrate is treated with the potassium thiocyanide. You are getting silver thiocyanide plus KNO3. So here what is happening, two insoluble salts when you are mixing together, one soluble and another is the insoluble salt. So insoluble salt is precipitating out. Okay, and the amount of silver present in the solution may be estimated volumetrically. Argentometry. Argentometry is nothing but it is the method amount of silver present in a solution may be estimated volumetrically is known as argentometry. There are three methods or three ways. One is Morse method, Fajan's method, Hole-Hart's method. Morse method. When silver nitrate is added to sodium chloride solution with potassium chromate as indicator, all the chlorides will be precipitated first, then silver forms silver chromate with permanent red color. You can see here equation silver nitrate. When you are treating with the silver nitrate you can see silver nitrate is treated with the sodium chloride, then you are going to get silver chloride and silver sodium nitrate, it is white precipitate is giving. Again after that silver nitrate is reacting with potassium dichromate and giving that silver chromate which is reddish precipitate. So you are finding permanent red color in this case. Next, Hole-Hart's method. In this method, unknown silver nitrate is titrated against potassium or ammonium thiocyanate. The indicator used here, ferric salt. First, all the thiocyanate reacts with the silver ions present in the and then ferric ion indicating formation of permanent blood red precipitate as the end point. You can see silver plus thiocyanate, silver thiocyanate white precipitate. Then ferric ion is reacting with thiocyanate and giving that ferric thiocyanate red blood color. Complexometric titrations. Titrations involving the use of complexing agents are known as complexometric titrations. The complex is coordinate with metal ions through several donor atoms at once, simultaneously forming several chelate rings and giving very stable complex. Generally 5.6 membered chelate rings are formed which are more stable. ADTA, ethylene diamine tetraacetic acid, disodium ethylene diamine tetraacetate is one of the most versatile complexing agent used in volumetric analysis. It forms very stable metal chelates with many metals. Hydrogen ions are liberated during the formation of complexes. EDTA has been assigned following formula. It has been observed from measurements of dissociation constants that two hydrogen atoms are probably held in the form of jitter ions. The other names used for EDTA and its sodium salt are trilon 13, complexone 3, sesquiterene, vercine, and keton 3. EDTA is considered to be the best complexing agent in quantitative analytical reactions owing to the following facts. It is relatively low price. The spatial structure of its anion, which has 6 ligand atoms, thus corresponding with the coordination number most frequently encountered among the metals. It forms stainless positive membered rings on chelation. It reacts with all cations, at least to some extent, carrying two or more positive charges with the exception of alkali metals. Some ions can be masked by using masking agents like cyanide. Hence, these ions may not react with EDTA. EDTA can be taken as a primary standard solution. The molecular mass of its disodium salt is 372.25. It precipitates in hot water and soluble to some extent in cold water. Almost all complexes of EDTA are soluble in water. It forms colored complexes with colored metal ions and colorless complexes with colorless metal ion. EDTA is represented as Na2H2Y, which gives complex forming ion H2Y2 minus. Solution. The reactions with the different cations may be written as below. Types of EDTA titrations. The important EDTA titrations may be direct titrations, back titrations, substitution titrations, or alkalimetric titrations. Direct titrations. The metal ion solution is buffered to the desired pH and titrated directly with the standard EDTA solution in order to prevent precipitation of metal hydroxide. Tartaric acid is added. The end point is determined using metal indicator. Back titrations. Several metals can be titrated directly because of either of the following reasons. They may be precipitated from the solution in pH range necessary for the titration. They may form complexes too slowly. A suitable metal indicator is not available. In all such cases of standard EDTA, solution is used, which after the reaction is back titrated with a standard metal ion solution. Example, chloride or sulfate of zinc and magnesium. The end point is detected with the help of the metal indicator, which responds to the metal ion introduced in the back titration. Next one is that substitution titrations. Substitution titrations are used for metal ions that either do not react satisfactorily with a metal indicator or for the metal ions which form EDTA complexes that are more stable than those of other metals such as magnesium and calcium. In practice, the metal cations to be determined is titrated against the magnesium complex of EDTA. Thus, the amount of magnesium ion is set free equivalent to the cation present and can be titrated with standard EDTA solution and a suitable metal indicator. Alkalimetric titrations. When a solution of disodium ethylene diamine acetate is added to a solution of metallic ions, complexes are formed with the liberation of two equivalents of hydrogen. The liberated hydrogen ions are titrated with standard alkali using an acid base indicator. Metal ion indicators. Several organic dyes can be used as indicators in EDTA titrations. These dyes form complexes with metal ions which are intensely colored. The amount of indicator added must be small so that only a fraction of metal ions present is combined in the color complex. Now indicators, among them urichrome black tea, it is also known as EBT, is one of the most important one. So you can see this about the indicator. The most widely used indicator is EBT. The sulfonic group of EBT gets ionized in aqueous medium, giving an anion which has a red color at higher pH. Peroxide or ammonium perchlorate. It is mainly used for titration of calcium at pH 12. Calcium is bound to in a 8-membered ring in the peroxide chelate. The larger ring confers a lower stability than usual 5 or 6-membered ring chelates. Hence, magnesium peroxide is less stable than calcium complex and can be estimated easily in presence of magnesium. Titration mixtures. EDTA is very unselective reagent because it complexes with +2, +3 and +4 charged metal ions. Thus, the several methods are employed to separate the two cations present in the solution but titrated against EDTA. Suitable control of pH. Controlling the pH of the solution makes use of the stability of metal EDTA complexes. Thus, a mixture of plumbous ion and calcium ions can be successfully titrated against EDTA using methyl thymol blue as indicator. Lead ions are titrated at pH 6 without any interference from calcium ions. Once the end point is reached, The pH of the solution is raised to 12 using sodium hydroxide. Then calcium ions are estimated by continuing the titration with EDTA. To 50 ml of the metal ion mixture, hexamine is added to maintain the pH 6. The solution turns blue. Now solution is titrated against EDTA. Endpoint is change in color of the solution to yellow. Addition of sodium hydroxide turns the solution to bright blue. Ion titration is continued until gray colored solution is obtained. Use of masking and demasking agents. Masking may be defined as the process in which a substance, without physical separation of it or its products, is transformed, that it does not enter into a particular reaction. Demasking is the process in which the masked substance reagents its ability to enter into particular reaction. The effective masking agent is cyanide ion. This forms stable cyanide complexes with cadmium, zinc, mercuric ion, copper, cobalt, silver, and platinum. It does not complex with manganese and lead. Thus, calcium, magnesium ions and plumbous and manganese ions can be determined in the presence of metals masked by potassium cyanide. The demasking is done using methanol, ethanolic acid solution of with chloral hydrate. Now separation of magnesium ions, zinc ions and copper ions. First add excess of EDTA to the mixture and back titrated with magnesium solution using EBT indicator. This gives sum of all the metals present. Treat the solution with excess of potassium cyanide and titrate as in step 1. This gives titer value for only magnesium ions and add excess of chlorate to the titrated solution in order to liberate the zinc from cyanide complex and titrate until the indicator turns blue. This gives only zinc. The copper content is found by difference. This is about the complexometric titrations, finding the different metal ions with help of EDTA.